Once we become familiar with someone, we start to feel quite comfortable, right? The formalities are reduced to a minimum and we can act more casually. Well, similarly, since we have become so familiar with complex numbers, why be so formal? We know how they look like. We can identify their real and imaginary parts. We learned how to perform different operations on them, represented them as ordered pairs, discussed the relevant properties, found the modulus of a complex number, practiced the concept with examples, even represented a complex number on a complex plane by making an Argand diagram. That's a lot. Not just that, but in the last few lessons, we saw the equivalent polar form of a given complex number too. Now, identifying the real and imaginary parts in this case is quite easy, right? But not if a given polar form is raised to some power. That power could be any positive or negative integer, except 0, because anything raised to 0 is equal to 1. So, if the power of the bracket is there, we know it is going to get expanded. And after the expansion, we would have a bunch of real and imaginary parts. Wouldn't it be a big mess to identify each of them? Would it even be possible to expand the bracket if the higher or negative powers are involved? No worries. Introducing the de Moivre's theorem. We are not proving this theorem here as it is beyond your scope right now. But applying it is sure a piece of cake. Simply multiply the given power to the argument of both sine and cos. And you are done. Literally. Now, if you have to find the real and imaginary part of this complex number with power n, all you need to do is to convert it into the polar form by using the formulas we studied earlier and take r common from this bracket. Since this power is applicable to both r and the bracket, apply it on each term individually. Now, on this bracket, de Moivre's theorem can be applied by simply multiplying n with the argument theta. Lastly, multiply r raised to n by both these terms inside the bracket. And finally, we have found the real and imaginary parts of the given complex number. Do you like it? Let's solve a similar problem with numerical value. The agenda is still the same. To find the real and imaginary parts of this complex number with power 3. Our recent experience says that we need the help of de Moivre's theorem for that, whereas the theorem needs the complex numbers in the polar form to be applied. As the first part of a complex number is considered to be x, and the part with iota is considered to be y, their polar representation will be this, right? So, we will write our given expression in terms of the polar coordinates. Now, we will take r common with power cube in the next step and apply the de Moivre's theorem, according to which the power gets removed and comes right here with the angle theta. Simple. Now, we have to find the value of the r and theta. For that, we already have the values of x and y equal to square root 3 and 1, as well as the required formulas to find r and theta. So, what are we waiting for? Just substitute the values and obtain r and theta. Then plug these back into the expression where we had left it. We get this, where 2 cube becomes 8, cos 90 becomes 0 and sin 90 becomes 1. And by multiplying the bracket with 8, finally our real and imaginary parts have been identified. Excellent work, students! That was easy for you, wasn't it? Now, why don't we raise the difficulty level and practice this theorem to find the real and imaginary parts of an expression that looks like this? Yes, that should be challenging. So, come prepared, my mathematicians, and I will see you in our next lesson.